Master year, sorry. Doctor, almost Doctor.
Hey.
Want us to clean the blackboard?
No, it's fine. I don't think I'll need it. If I need, I'll just use a little bit. Yeah, no worries.
A lot more to do there. Yeah. Not only from like just designing an algorithm, but in terms of classification phases. Yeah. Whether a given state is not favorable. Yeah.
Okay, we should start. Second lecture by Giulia.
Okay. Thank you. Okay. So yesterday we introduced this platform based on neutral atoms. So first of all, I wanted to hear if you guys had more questions about what I said yesterday, anything that wasn't clear that you still have questions about, so that we can start from there. All good? Okay. Let me make a quick clarification that I realized yesterday from a question that wasn't completely clear. So yesterday I showed you that you can do different things with these Rydberg atoms to engineer different kinds of Hamiltonian. What I mean with this is, you know, this defines what's the kind of coupling that you can have between the atoms. So you can define what's the type of interaction. Of course, then you can be creative, and if you introduce anisotropy or if you play some tricks, then the range of Hamiltonians, of course, expands, and we're going to see some of these today. But this is just to clarify. This defines what are the types of interactions that we can introduce, and then what you do with that, it's up to your imagination. Okay, so today we want to look at some experiments that are in the context of quantum simulation using Rydberg atoms. So just a disclaimer, there were many things that I would have liked to talk about in this past, let's say, 6 years. There have been really a lot of different experiments in this context of quantum simulation with Rydberg arrays. I picked a few that I think are representative of different things that you can do, and that can show you what are the kind of measurements that you can do, how you can tune and engineer the system to get to interesting regimes. Of course, it's not a complete survey of everything that has been done. I'll try to put in the slides all the relevant references to other works that you might want to look into. Okay, so yesterday we ended on this note saying that you can use this programmable quantum platform in 2 or 3 ways. So you can do analog, you can perform analog quantum dynamics, or digital, or use a digital approach. And when we talk about quantum simulation, we typically use this first approach, the analog mode, or a little bit of the hybrid. And towards the end of the talk, hopefully, I will get to show you an example of this. Okay, so let me first generally introduce what we mean when we say that we're using this platform in an analog mode. So I will show you an example that then is going to be useful for everything we see today. So we take as a first example this square lattice that I showed at some point yesterday as well. Now, we know that if we couple all the atoms to the Rydberg state using laser light, we have these Rydberg interactions that arise between the atoms. And I told you yesterday about what's the Hamiltonian that describes the system. So we have this Hamiltonian. We can consider now, for example, this simple case where we tune the blockade radius such that if you have an atom in the Rydberg state here in the center, its four nearest neighbors are all blockaded. Okay, so in the presence of this coupling to the Rydberg state, if you get a Rydberg excitation, its four nearest neighbors are all blockaded, so they cannot be excited at the same time. And so let's say that in this condition, we look at the ground state of the Hamiltonian as a function of the parameter delta. So delta, just to remind you, is the detuning of your laser from the resonance, so from the transition from ground to Rydberg. Okay, so we can look at two opposite regimes. When you go to large negative detuning, so you're down here somewhere. Now what you have is that you don't have enough energy to excite atoms to the Rydberg state. So the many-body ground state is the trivial state where everything is in the ground state. Okay, clear up to here. Okay, so this is trivial and also kind of boring. But if you tune delta to large and positive detuning, like this, then what you want to do, if you look at the Hamiltonian here, this term is negative. So what you want to do to minimize the energy is to maximize the number of atoms in the Rydberg state, right? This term here is like a chemical potential. So in this situation here, where the blockade looks like this, you cannot excite the four nearest neighbors. So the solution with the maximum number of excitations to the Rydberg state is this antiferromagnetic state, where you have every other atom is excited to the Rydberg and the other ones are in the ground state. Does this make sense? So you're trying to do a dense packing of Rydberg excitations, provided that you have this constraint that comes from the blockade. So in this regime here, for this Hamiltonian with this specific blockade radius, this is the many-body ground state at large detunings, large positive detunings. Now, okay, so this is the idea of the blockade radius. So we can do this in the experiment. This is a picture. This is an actual snapshot from the experiment, where here we're marking the Rydberg atoms with these red circles. Just to remind you, I mentioned this yesterday, but I wanted to write it down somewhere. When we do the readout, the way we read out the states of the atoms is we do fluorescence imaging. So we shine resonant light on the atoms so that we can detect what atoms are there. And since the Rydberg atoms are not trapped in the tweezer, they are anti-trapped, they get lost. And so we detect them as losses. So here, these red circles are just to identify the places where we have a missing atom, okay? So we can do this in the experiment, but how do we get to this state? How do we prepare it? How do we initialize the many-body system in this state? We typically use a quasi-adiabatic state preparation. So here, it's a clear example of what these analog quantum dynamics mean. We have a few knobs in the system that we can tune, and we tune them continuously to do this quasi-adiabatic state preparation. And in particular, what we do here is the following. So we prepare our array of atoms in the square lattice in this case. Then we slowly turn on omega, which means we slowly turn on the lasers that couple the ground to the Rydberg state. And we start initially with a large negative detuning. So initially we're in this situation here. This one corresponds to the state where the atoms are before you do any Rydberg thing. So we're able to prepare this with very high fidelities. And then what we do is we slowly tune the detuning. So we go from this situation to this one, so that we try to connect the initial trivial ground state to the more interesting, more complex ground state at large detunings. And this is the idea of a quasi-adiabatic state preparation. If you do this slowly enough, the system will follow in the ground state of the Hamiltonian at each time, right? Are you familiar with this idea? Okay. So of course, we cannot be perfectly adiabatic, especially for large systems like this, because the gap at some point becomes very small, and so you would have to go infinitely slow. But if we do this slowly enough, we can do this state preparation with fairly high fidelities. And if you notice here, the shape of this ramp is not linear, it's actually a cubic function. And the idea is you want to be the slowest when you're crossing the minimum gap region. Okay, so this is an, yes?
Why will text not turn off?
It's not turned off. We turn it off before, yeah, I mean, it is turning off. I think it's not really visible. We turn it off at the end before taking the picture. But in principle, yeah. Mm-hmm. With what? Oh, with the adiabaticity? Well, I mean, you have some limitations in the experiment. You cannot go at super large omega. No, but if you go to I mean, this system is already pretty large. These are 256 atoms. The gaps are already fairly small, but if you, I mean, the larger the system size, the smaller the gap gets. So at some point, you're bound to be non-adiabatic, non-perfectly adiabatic, let's say. Yeah.
I thought you were actually good with the gap in some cases, at least in the ideal situation. I compare all these topological order states. There is a case. Right?
Yeah, in some cases, you really have a phase transition. Yeah, for sure. Yeah. Yeah. Sorry, can you say that again? So they are trapped until we turn on, as I mentioned yesterday, as soon as we start to excite to the Rydberg state, we turn off the traps. So the trick here is, as you see, these time scales are just a few microseconds. So in those time scales, the atoms don't really move. Okay, yeah. Mm-hmm. Yeah. I wish I had 1,000 qubits. So yeah, at some point we're gonna get into that regime where it becomes problematic. As Leo was saying, of course, it's a game between how large the Rabi frequency can be and what's your coherence time. So you want to have a large enough Rabi frequency such that you can, within your coherence time, you can do something that is kind of adiabatic. Yeah, I mean, even in this case, we're not perfectly adiabatic. We do see that we're not perfectly in the ground state. We have some excitations. You will see many examples of this. But yeah, that's certainly a problem. I mean, this is not the only way you can prepare a phase. There are other ways. But this is the one that has been used the most, at least so far. Yeah. I mean, there are these shortcuts to adiabaticity that you can use. We did something kind of on that line at some point in an experiment where you do some, you do these optimization, use these optimization algorithms to try and find some shortcut. Or, I mean, in these cases, for example, let's say that you want to prepare the checkerboard phase like here, you can just shine some local detunings to make sure that those atoms get excited to the Rydberg state and the other ones don't. But of course, that works for these kind of phases, but if you want to do something interesting like a topological phase, that doesn't work anymore. You need to find something smarter to do that. Okay. Of course, so here I just wanted to show you an example of what an analog quantum dynamics looks like. But another thing that you can do, for example, is to do quenches. So all of a sudden you change some of the parameters to quench your system out of equilibrium. So this is, the kind of tools that we use when we do analog quantum dynamics. But now let's look at the type of experiments that we're going to look at today. So we're going to look at some many-body phases. So these are, I would say, these three categories. I think, yeah, they should take into account everything that has been done with Rydberg atoms. I might be missing something, but in terms of quantum simulation, I would say that these are the three categories that have been explored so far. So the study of some many-body phases, and we're going to look at some partially ordered phases and some topological phases. We're going to look at one specific example of quantum phase transitions that has been studied. And finally, we're going to look at some quantum dynamics, hopefully, if we manage to get there. Okay, so we'll start with the easiest case, I would say, which is study of conventional, so-called conventional phases. So here, again, we're looking at the square lattice. I showed you that in this case where you have this type of blockade radius, the ground state is a checkerboard. So it's the antiferromagnetic state where you have every other atom in the Rydberg state. But what happens when you change the blockade radius? Okay, if you go smaller, nothing interesting because nothing is blockaded. But what if we go larger? So we start blockading more and more atoms. So this was studied in this theory paper where they mapped out the phase diagram of the square lattice as a function of the detuning delta and as a function of the blockade radius. So this is the ratio of the blockade radius over the lattice spacing. Okay. And so here you see there are some other phases that occur, and we can probe this in the experiment. So here you see our usual checkerboard pattern. Then you have these two other phases that we looked at into this paper here. So this one that is called striated, you have a star phase and so on. Some of these are kind of, so for example, the star phase, again, is the dense packing of the lattice, provided that you have a larger blockade. The striated phase instead is kind of a stranger phase. It's more quantum, I would say, because you have some sites in which you have a fractional occupation of the Rydberg state. I won't go in the details of this, but here I want to show you more what are the tools that we can use in this case to explore the phases that we prepare. So let's say we do the same procedure. So we do this quasi-adiabatic state preparation, and we go to different points of the phase diagram to map it out. At this point, how do we characterize the state that we have prepared? Okay, so the first, let's take the checkerboard phase as a first example. The first thing that we can do is to measure its correlation function. So this is the correlation function that we're measuring. You measure the product of the density at two positions minus the average of the densities. Okay, so here you can average. For each snapshot, you average over different positions along the array, and you average over different experimental repetitions. And so what you get is something like this. So if you had a perfect checkerboard, you would see this pattern that just alternates between 0.25 and minus 0.25. Here we have something pretty good, but with some decay. And so one thing you can do here to see how well you're able to prepare this checkerboard phase is to measure the correlation length. So you just average this along the vertical and the horizontal direction, and you measure the decay of your correlation function to determine what is the correlation length. And so here we have the lattice we're using is a 15 by 15 lattice. And here you see that our correlations extend over about 11 sites. So it's pretty good. Okay, so this is one example, but to define to look at the correlation function for these other phases is not as useful. So we do something else. We look at the Fourier transform of single shot measurements. So we take these shots, this corresponds to 0 and 1s, and then you do the Fourier transform of that. And so for example, for the checkerboard phase, this is a theoretical Fourier transform. You see something like this, where you have a single peak at the center at pi. And this is basically, this corresponds, the amplitude of this peak correspond to the canonical order parameter for an antiferromagnetic phase, which is the staggered magnetization. So if you measure the amplitude of that peak and you measure the staggered magnetization for this phase, you get the same thing. So this gave us an idea, which is we can construct order parameters for all the other phases in a similar way. So we look at the theoretical Fourier transforms for these phases. We look at what are the peaks that define that phase. Those peaks basically tell you what is the kind of ordering that you have in the array, right? At which frequencies do you have the atoms in your array? And so we look at these peaks to construct order parameters for those phases. And so what we do at this point is we can map the full phase diagram defining these order parameters for these three phases, for example. So in the checkerboard, we just measure the difference between the peak at pi minus the peak at pi 0. For the striated, we find another thing, and for the star and so on. So you just define what are the Fourier transform peaks that you care about. And so you can basically reconstruct these lobes, but for the experimental data, right? So this is what we observe. So you already see that this kind of looks like this. But we can do the exact same thing in the numerics, and you see that what we find in the two cases is quite similar. So yeah, we can say from this how well we are mapping that phase diagram that we know from the theory. Yes. Mm-hmm. Yes. So on each shot, you average over different positions, between sites at the same distance, but then you also average over many different experimental repetitions. It's at least thousands of data for each point. Yeah. Yeah, it's again, so here maybe I'm cheating a little bit. I'm showing you the best, the best single shot that we get. We get it a few times, this one or the complementary one, but typically you will find some defects. And this is again, because you're not perfectly adiabatic. So you have some finite correlation lengths. So you get this if you have enough time to spread your correlation throughout the array, but sometimes you're not. Mm-hmm. No. I mean, we do get both Ising configurations, but then we also get a lot of images where you have some defects here and there, where you have some domains. Yeah. You have some domain walls along your image. Yeah. I mean, of course, there are other things that come into play, like you can have readout errors. You can have, during your state preparation, you have some chance of having the coherence of some of the atoms. So there are many things that come into play, but the non-perfect adiabaticity is the main cause of that. I mean, if we take a smaller array, we get much better, right? Yeah. So that tells you that it's an adiabaticity problem. Like when you increase this, it becomes harder to spread your correlations throughout the whole size of these bigger arrays. Okay. Yeah. Mm-hmm. Yes. So the easiest way of controlling it, let's say that it's fixed, you just change the lattice spacing. So you change what's the distance between the atoms, and so you will get more atoms that get into the blockade. Sorry, this circle. Okay, just to clarify, these circles are the Rydberg atoms. In this case, they're not the blockade radius. Yeah, sorry. I'm never showing this, but for example, in this case, you're getting the diagonal atoms into the blockade as well. In this one, you're getting the diagonal atoms. In this one, you're getting the next nearest neighbor. So you're increasing the blockade radius. You're getting more atoms inside the blockade radius.
But like, are you able to do this? So like, here it looks like you can do this. Like, it doesn't matter which site you're looking at. They all act the same. But you were saying that you do best.
Yeah. For each of these, we took the best. Yeah. We definitely took the best snapshot for each of these, just to be representative. Mm-hmm. I mean, V the interaction potential. I mean, it's approximately like very large within the blockade radius and smaller outside, but it's this 1 over r to the 6 potential, right? So it's not. It's much larger than omega. Yes. Yeah.
Okay, but maybe
the critical value of delta doesn't really depend on those parameters. It's just the physics of the system. Yeah. You mean where the transition happens? Yeah, yeah. It's a critical ratio. Yeah, if you change omega, it changes the position, but the relative position with respect to delta is to respect to omega is always the same. No, interaction enters in this direction. It's on the vertical axis here. Yeah. Okay. Okay. So now, so this is more or less it. I just wanted to show you a little bit what are the tools that we can use to probe this type of ordered phases, where basically what you're trying to define is an order parameter that you can measure from your measurements in the Z basis. Okay, so this is what we did here. I want to show you that there was another experiment that the group in Palaiseau did more or less at the same time, where they did kind of the same thing. So they studied this antiferromagnetic phase, not the whole phase diagram, but in particular the antiferromagnetic phase. Maybe it's interesting to see that they did a different type of state preparation, again, trying to perform this quasi-adiabatic protocol, but taking a different trajectory to get there. And here they do a very detailed characterization of the antiferromagnetic phase they prepare, but also they look at the extension of this study to triangular lattices. And so they look at the correlations in this case, and they try to define what are the phases that they're observing. I'm not gonna give you much details here. It's more or less the same idea. So you can look at the paper if you're interested in the details. Okay, so with this, before switching to topological phases, I want to show you that within the same experiment, so again, looking at square lattices, there was also a study of phase transitions in that case. So here, the phase transition that we're studying is the transition from the disordered phase at low detunings into the checkerboard. And the way we study this phase transition is by sweeping into the checkerboard phase with different sweep rates. So in this case, instead of doing the cubic sweep that I showed you before, we just go simple. We just do this linear sweep, but we change the sweep rate. So we change how fast we go into the phase. And of course, slower sweep rates, as we were saying before, mean that we're more adiabatic and that the correlation length at the end becomes larger. And so you see here the data of the correlation length measured at different final detunings and as a function of the sweep rate. So this is the slowest, and this one here is the fastest, and you see that the correlation length doesn't grow as far as for the faster here. Okay, so here what we want to do is study the universality class of this phase transition. So I guess you're mostly theorists, so you know these things, but quantum phase transitions fall into universality classes, and these are characterized by critical exponents that determine a universal behavior of the system near the quantum critical point, independent of the microscopic details of the Hamiltonian. In particular, so for example, these critical exponents can define how the gap closes at the critical point, or how the correlation length diverges again at the critical point. In particular, the transition that we're studying, the one from the disorder to the checkerboard phase, is predicted to be in this 2+1D Ising universality class. And so we would like to measure these critical exponents to check that we're indeed in that class. And the critical exponents that are predicted for this class are Z equals 1. The Z is one of these two, and nu equals to 0.62. Okay, so how do we measure this? We use the quantum Kibble-Zurrer mechanism. So the idea is that we study how the correlations build up dynamically when we do these sweeps, and use the Kibble-Zurrer mechanism to measure these exponents. So in particular, this Kibble-Zurrer mechanism predicts a universal scaling between the control parameter delta that we're tuning during our sweep and the correlation length. You need to rescale this with the sweep rate. Maybe here it's not super interesting to go through the details, but the idea is that if you rescale this data with the sweep rate, you should see that these collapse onto each other. And so basically what we do here is we assume that z is equal to 1, and we try to measure nu. And so we change nu to see when these data collapse onto each other. And so this allows us to measure the exponent that we measure as 0.62, which is close to the theoretical point. And this was the first observation, was the first experimental observation of this 2+1 de-Ising phase transition, even if it's been known in theory for a very long time. I think it was never measured in the experiment. Yes? Yeah. So the fact that you have a limited correlation length, it means that you have a lot of domain walls, right, in your system. So it's like you have small patches of antiferromagnetic ordering, but you have a lot of domain walls in between. Yeah, exactly. This Kiboswary mechanism tells you that the growth of these domain walls is related to the sweep rate that you use to go into the transition, which is why you can extract the critical exponents from this kind of measurement. Yeah.
I'm confused by something possibly basic. So is this correlation extracted from the connected or disconnected correlation?
Remind me the definitions. Yeah. It's the one we're subtracting, which is the connect.
If that were the case, wouldn't I expect that the correlation should have a peak here to the critical point and then go back down to the other side?
So what I'm plotting here is exactly what I showed you before. It will take me forever to get there, but so it's exactly this, right? So this is what we're measuring. This is, how it looks like, and we're just taking this decay and fitting what's the correlation length, right? So you expect this to grow as you go deeper into the checkerboard.
But if I was in a perfect checkerboard, wouldn't that be the correlation?
It would be infinite. I mean, it would be flat here, right?
Because you're going into a definite product.
It's like one? I mean, it would be flat at 0.25, right? If you're in a perfect checkerboard. Why would it decay? As a function of distance? Why wouldn't it just be 0.25? Why would it be 1? If you're subtracting it. Yeah, which is why, sorry, maybe here actually this is okay. So here you take this and you take the absolute value. This is probably wrong, because otherwise you would have 0.25 minus 0.25, etc. Here it's just everything is positive. But yeah, you would get a flat thing. Maybe we can talk more about this later. I might be confused about definitions, but yeah, so when you're in the checkerboard here, you would expect this. For our definition, you would expect this to be flat. Maybe then we can discuss what's the definition we're using. Okay, maybe let me do this. Okay, so so here what we did was to find the critical exponent that allowed us to collapse these different data sets onto the same curve, which allowed us to measure this critical exponent, which is very close to the theoretical one for this 2+1D Ising transition. And again, this seemed a trivial result. We found out that it was kind of a new experimental result, even if for something that in theory was very old. Okay, this is it, I think, for this. Yeah. Okay, so now we switch to topological phases. This is the part that I'm going to talk more about. I think also, given the topics of these days and the interest that I saw in the audience, maybe it would be the most interesting for you guys. So the first one that I want to mention, this is going to be just one slide, but the first work that tried to tackle topological phases using Rydberg atoms explored this SSH model. Sorry, wrong slide. So here we're using this dipolar interactions that I showed you yesterday. So when you have two Rydberg states that have this kind of flip-flop interaction, as you see here. So this is from the group in Palaiseau. So here you are preparing your states, your atoms in these two Rydberg states that are coupled by this dipolar exchange interaction. You can understand this flip-flop interaction as hardcore bosons that are hopping along the chain. It's like looking at the p excitation. So when the atom is in the upper Rydberg state, and look at that hopping through the sides of your array. And here the interesting thing that are using also is the fact that this interaction is anisotropic, right? As I mentioned yesterday. So if you prepare the atoms in this quasi 1D chain, you have the interactions along this along this direction here are much stronger, and along this direction they're basically zero. So by tuning things in the proper way, you can map these into this bosonic SSH model. Here I'm going to be very superficial, but the idea is that they observe this fourfold ground state degeneracy due to the edge state of the chain, and they do some measurements to test the robustness of this symmetry protected state. That's about it. Again, if you want to see more details, you can look at the paper. Here, I just wanted to show you, this was the very first work on topological phases, and it used this XY type of Hamiltonian and used these asymmetric interactions in an interesting way to map into this specific model. But the one that I'm going to talk about more is this quantum spin liquid paper. I guess everybody in this room knows what a quantum spin liquid is. Anybody who doesn't? Good. Okay. I'm gonna explain it. Okay. So a quantum spin liquid phase, I mean, it's interesting because it's a topological phase, and it's closely related to the toric code that you've been hearing about a lot in these days. It's the same type of topological phase. So what was the idea of the original proposal? So this is a phase that was proposed by Anderson in the 70s. And what he was looking at was spin 1/2 particles with antiferromagnetic interactions again. So they want to be anti-aligned on a frustrated lattice like the triangular lattice, for example. So having frustration means you want neighboring spins to be anti-parallel. But if you choose the orientation of two of these spins, you see that you don't know what to do with the third, because in either case, it will be parallel with one of its neighbors. Okay, so what he proposed in this paper was, what if the electrons on this lattice form entangled pairs, also called dimers, where the state of the pair is a superposition of up-down and down-up, okay? So all the spins in the system would form this, would pair up with their neighbors in this way. And you can immediately see that you can have multiple ways of pairing the spins up with each other. So you have an exponentially large number of configurations that do this. And so in his proposal, the many-body ground state of this system would be the so-called resonating valence bond state, which is the macroscopic coherent superposition of all the possible dimer coverings of your lattice, okay? So this was his prediction. For a few years, nobody cared. But then people realized that there were a lot of interesting features of this phase. The first and obvious one is that this phase has long-range quantum entanglement. And together with it come the topological properties. Now, this is something that people have tried to find in experimental systems for a very, very long time. And what happened at this point, almost 3 years ago, is that some people at Harvard started to look into the possibility of realizing an analog dimer model for this phase using Rydberg atom arrays. So the idea is the following. Let's take the triangular lattice. And in this case, we put our atoms, so our spin degrees of freedom, not on the vertices, like in this case, but on the links of the triangular lattice, sorry. So all the atoms are placed in this way. And then let's say that here we have a Rydberg excitation. Then we have a blockade radius. So let's take the blockade radius like this, pretty big. Everything in the blockade radius cannot be excited. So the next excitations will be outside of here. Okay, so this is an example of dense packing of Rydberg excitations, provided that you have this blockade radius. Now you can do this mapping and say, what if I map each of these Rydberg excitations into a fictitious dimer that connects the two adjacent vertices of the triangular lattice? Again, this is not a real dimer. In this case, the dimer was made of two spins that were in this entangled pair. In this case, this is just a representation for our Rydberg atom. But the interesting thing is that you can see that the position of the dimers in this case is exactly the same that you have here on the left, meaning that the spatial constraints that you have between the Rydberg atoms in this case is the same that you have here on the left when you're trying to pair up your spins. Does it make sense? Okay, so here the idea is you want to pair up one spin only with one other spin. And in this case, because of the blockade radius, you have that each vertex of the triangular lattice can only be connected to one Rydberg excitation. So basically you have the same constraints in these two cases, which also means that you have exponentially many dimer coverings of your lattice with Rydberg atoms in this case as you had in that case. So again, the many-body ground state will look at something like this. So again, you have this macroscopic superposition that is the crucial element of the spin liquid. And this is an idea that was developed, as I said, by two different theoretical groups at Harvard, where they developed different types of dimer models using the Rydberg blockade. And in both of them, there were some hints of potential spin liquid phases. The one that we worked on in the experiment and that actually proved to have a pretty robust spin liquid phase is the second one from Ashwin Vishnovat's group. Okay, so how does it look in the experiment? It's not actually a triangular lattice, it's a Kagome lattice. And so you see the lines here that I drew correspond to a Kagome lattice, but again, the atoms are on the links of the lattice and not on the vertices. Okay, and then we need to tune the blockade radius in such a way that we can create this mapping to the dimer model that I introduced before. So again, what we want is that for each atom in the Rydberg state, its 6 nearest neighbors are blockaded. And we can do this, again, as I said before, you can tune the blockade radius and decide how many atoms end up inside it. And as I mentioned, these correspond to a dimer model, in this case, a dimer model of the Kagome lattice. So when you have a dense packing of excitations here, you have a density of 1/4, and you have that each vertex of the Kagome lattice is only touched by a single dimer. Okay, so that's the model. And in the numerical simulations that they did in this paper here, they saw that there is indeed a range of parameters in which there is a quantum spin liquid state that again is the superposition of all the possible dimer coverings of this lattice. So this is exactly the analogous of the resonating valence bond state from Anderson's prediction. Okay, yeah.
sites everywhere, and there are no vacancies. Here, you fix the wholesale.
Okay. I didn't follow you, but okay. Yeah, exactly. So the only thing that you're missing is that these dimers are not actual dimers, but it doesn't really matter because the long range entanglement and the topological properties come from the fact that you have this macroscopic superposition. Yeah, exactly. So yeah, in some sense, yeah. Yeah, it's still the same Rydberg Hamiltonian, but on this geometry, that's what it generates. Okay, so what we do in the experiment is exactly the same thing that we did before for the simple square lattice. So we do this quasi-de Batiste preparation, and we find, and we look at the final state that we prepared. Here, what we're doing here is we take the snapshot. Here I'm drawing the Rydberg atoms instead of using the usual red circles. I'm using the dimers to map into this model. But here you can immediately notice a couple of things. The first one is we're in a pretty good dimer phase. So to be in a dimer phase, what I mean is the density is exactly 1/4. And so I expect all the vertices to belong to one and only one dimer. And this is the case almost everywhere. You see we have a few defects here and there, but it's pretty good. And second, what you expect for this spin liquid phase is that there is no obvious spatial ordering. You don't want to have any spatial ordering because this should look disordered. Okay, so now how do we characterize this? Of course, it's much more complicated than for the ordered phases from before. So first thing, again, as I mentioned, we do this quasi-de Batiste preparation, same thing as before, only this time, and negative detunings, we are again in the trivial state where everything is in the ground state, and a positive detuning, we should be in the spin liquid state, at least we hope so. So the first thing we can measure is, again, we do the sweep and we stop at different final detunings and we measure the density of Rydberg excitations. So what we expect is that, this should grow, and when you enter the spin liquid phase, this should sort of saturate around 1/4, which is the maximum filling. So it looks like here we should expect to see the spin liquid potentially, but of course this is not enough. We need to be able to measure the topological properties of this phase. So what we want to measure are these. So you want to be able to measure the topological correlations that are particular of this spin liquid phase. And the thing about topological phases is that there is no local observable that can help you identify the spin liquid. So we want to measure these string operators. Again, this is the same thing that you've seen for the toric code in these days. So these string operators are just a string of single particle operators. So this is the toric code again, but we can define something analogous for our model, and I'm going to show you how they're defined. So we have two types of topological operators, of string operators. One is Z and one is X. So the Z operator is defined like this. So you have this string that crosses the links of the Kagome lattice. So it crosses the position of the atoms. And along this string operator, you're measuring the parity of dimers along the string. So the idea is every time you cross a link where there is a dimer, you get a -1. Every time you cross a link without anything, you get a +1. So if you take the smallest closed loop of this Z string operator, the expectation value for a perfect dimer phase should always be -1, right? Because I said before, a dimer covering is the one where each vertex belongs to one and only one dimer. And so every time you do this, you should find exactly one dimer, so -1 expectation value. Okay. Now you can extend this to larger loops like this. And the expectation value that you expect, again, when you're in a perfect dimer state, is -1 to the number of vertices enclosed, because for each vertex you have a dimer, and so for each dimer you have a -1. And so depending on whether you have an even or an odd number of vertices inside, you will get +1 or -1. Does this make sense? It's very important. Okay. Okay, so this can help us define if we are preparing our atoms in a dimer state or not, which is the first thing that we want to check. So now what's the very nice thing of this experiment is that we have access to these measurements where we can really look at each individual atom. And so from these fluorescence imaging shots, we can really look at each atom and measure the string operators, right? Because the string operator is just, we can detect how many dimers are there, and we can measure the expectation value for the string operator for each repetition of the experiment and averaging over different locations along our array. So this is what we observe. So what we see is that for negative detunings, you have, so here we're measuring for two different loops that look like this. The red one encloses one, let's say, hexagon of the Kagome lattice, and the green one encloses two. So for both of them, we have a positive expectation value at negative detunings. And this is a trivial result of the fact that if you have a very low density, most of the time when you measure these loops, they're not crossing any dimer, right? So you have +1, +1, +1. So it's typically, the expectation value is typically +1. A few times you're going to cross 1. And so the expectation value here is not perfectly 1, but it's somewhat lower than that. But this is a non-interesting result. But then what we see is that as the density grows, this average is down to 0. Because when you're in a phase that has some density that is not 1/4 yet, you have basically 50% probability of measuring +1 or -1. But then when you get to this 1/4 regime, you see that the expectation value grows for both, but they have different signs. The reason is in this loop, we have an even number of vertices inside, whereas in this loop, we have an odd number. Okay, so if this was a perfect state preparation, what we would expect is that here we go to +1 and here we go to -1. The fact that we observe something finite means that we have an approximate dimer state. And again, we can zoom in this region and measure for loops of different sizes. So we go bigger and bigger, and we see that we have a finite expectation value for all these loops, and the signs match with the parity of the vertices inside. So here the conclusion is we're observing a transition into an approximate dimer phase, where the word approximate is important. Yeah? Mm-hmm. Sorry, I couldn't hear the last part. Mm-hmm. So, I mean, so here, so here you're taking a snapshot. Every time you take a snapshot, you're averaging over different locations of the loop, and then you're averaging over many, many shots. And the reason, I mean, these expectation values look bad, but actually the state preparation is not that bad. But the reason is this kind of observable is very unforgiving, because if you have just one error, your expectation value just flips. It's not like it's slightly smaller, it goes to -1, right? So any error you have hits you very bad. I'm gonna show you later what kind of errors we have and how we study that. So maybe we can get back to your question in a few slides. But okay, so the conclusion for now, I hope it's clear, is we measure this Z operator to identify if we're preparing the system in a dimer state or not. And from these measurements, we can say we are in an approximate dimer phase, which means we see the right type of correlations, but they're not as high as if we had a perfect dimer state. Yeah. Mm-hmm. So you should saturate at a quarter in a perfect world in which you cannot violate blockade, but in practice, you can violate blockade. If you increase delta more and more, you're basically paying for that energy penalty to violate blockade, and so it doesn't saturate. It doesn't saturate because you're allowed to go beyond blockade. So there is a window in there in which you're expected to have the spin liquid, and it's not. It doesn't go. It doesn't keep going. It's just. Yeah. So the density, yeah. So you see the 4 here is basically where you have this peak. The spin liquid extends a little bit further. You don't need exactly 1/4. Those properties remain even if you're slightly above or below. But yeah, you should be in that. It should be there. Okay, so now the tricky thing is, of course, this is not enough. This tells us that we have the right type of correlations. But the thing that is most important to detect that this is a spin liquid is to figure out if we're actually preparing these macroscopic superposition of dimer states, right? So we want to measure coherence, which is what the second string operator will allow us to do. So we define this second string operator, X, which is, here things get complicated. So it's defined as follows. So this is off diagonal. Now, in the Kagome lattice, you have, you can see that you have these hexagons and you have these triangles, right? Okay, maybe here it's larger. So you have these triangles. We define the string operator on a single triangle. So if we apply X on this side of the triangle, this corresponds to creating a dimer if there is nothing on the triangle, or removing the dimer if you have one dimer on that same site. But if you have dimers on the opposite side of the triangle, you're swapping their position. This is just a definition, nothing more. But now, an interesting thing is, let's say that we apply this, we take this definition and we apply the X operator along the hexagon of the Kagome lattice. Now, what you see is that what this X operator does when you apply it on a closed loop is to map a perfect dimer covering into another perfect dimer covering. So for example, if you take this, where you have these 3 dimers, you apply the X operator. So here you're gonna remove the dimer, you're gonna create one here, remove this one, create one here, and so on. And so you get into this complementary dimer covering. Same thing here, you apply X on the hexagon, you're gonna swap the position of all these dimers and end up here, if you do it here, and so on and so forth, okay? So what the X operator does when you apply it on a closed loop is to transform a perfect dimer covering into another dimer covering. So you stay within the dimer covering subspace, but you transform one into the other. And so this means that if you measure X on closed loop, and you find an expectation value that is finite, this is a signature of coherence in your state between different dimer coverings. So let's say that your original state had these 3, okay, let's say it was an infinite superposition, but it had these 3 states inside. Then when you apply the operator, you're getting the other 3. But if you just had one of these into the superposition, when you measure X, then you have an expectation value of 0. Does this make sense? Okay. So here is the interesting thing. If we measure X operators, we should be able to detect if we have coherence or not. The problem is, how do you measure this off diagonal strange operator? Turns out that there is a way of doing this. So this is a clever idea that Ruben from the theory group thought of. You can do a basis rotation in the following way. Measuring X on a certain string corresponds to measuring Z on the dual Z string. The dual Z string is defined in this way. If you're measuring X on this side here, it's the Z string that crosses the 2 opposite sides of the triangle. After doing a quenched time evolution of your system, where you reduce the blockade radius to only cover the 3 atoms in a triangle. This is something that for now you're going to have to take for granted because it's something very unintuitive, and the proof of this is a mathematical proof. There is no obvious intuition, physical intuition, but the idea is you take your initial state, you perform this quench where you need to change the blockade radius, and after that you measure in the Z basis on specific dual strings, and that is going to give you the same expectation value as the original X string that you wanted to measure. Okay, here you need to trust me a little bit. So what we need to do to be able to apply this quench is, as I said, we need to change the blockade radius. And we can change the blockade radius by changing omega. So yesterday I told you that the blockade radius is defined as that radius at which the interaction energy is of the same order of omega. Okay, so if you change omega, you're changing the blockade radius. And here's a tricky thing that the few experimentalists among you might appreciate. If you need to change the blockade radius by this quantity, it means that you need to change omega by a factor of 14, which means that you're changing the laser power by a factor of 200. So this is one of the most challenging experimental things that I've ever done in my life. But we figured out a way to apply this quench. So you do your state preparation, which is this part here, and then you apply the quench, and then you measure the X operators. And these are the final results. So again, here, all we want to do is that, all we want to see is to observe a finite expectation values for these X loops. We measure on loops of different sizes again, and we do observe that there are these peaks that we observe even for larger loops, which tell us that we have some coherence in the state that we're preparing. Yes. Very good. Yeah, very good question. So there is a detail in how these string operators are defined, for which it can have a finite expectation value also in the phase right before the spin liquid. To show you this, maybe we can come back to this later. But let me just say that for now, what I'm going to tell you is we want to make sure that in our spin liquid, both of these expectation values have the proper value. So we need to take the overlap of these two features that we've seen. But also, I will come back to that. I need to find a quick way to explain it. But also, if you notice so far, I made some very qualitative comments. I'm just saying these need to be finite, but what does that actually mean? We would like to have something quantitative. So the question is, can we define some order parameters for this phase? And so a more precise and quantitative way of looking at this is to compare the expectation values for these string order parameters between closed loops and open strings. So for example, if you look at this data here, so here I'm plotting the expectation value for a closed loop for the Z string. So this is the same data that you saw before. And for an open string that corresponds to half of that closed loop. So what you see is that in this trivial region that I identified before, where the expectation value is finite for trivial reasons, both of them have a finite expectation value. But when you go into this dimer phase, the open string goes to 0. And a similar thing happens for the open strings. And this kind of goes back to the question about why is the peak shifted. So what we see here is that the expectation value for the X string, the open one, is finite over this range of the tunings, and then it goes down while the closed loop stays finite for a broader range of the tunings. So here there is some trivial phase that is allowed to have finite expectation values for X, but it's not the spin liquid. Okay, now what we want to do, so as I was saying, the closed loops, from this we can see that the closed loops are the ones that detect non-trivial topological correlations, whereas the open strings can help us distinguish the spin liquid from nearby phases, as we did here. So a more quantitative way of looking at this is to define these string order parameters that are defined as the ratio of the expectation value for the open string over the square root of the expectation value of the closed string that is just twice the length. Okay. So what we expect, so these are the three phases that the theory predicts. So you have this spin liquid in a certain range of the tunings. At lower the tunings, you have a trivial phase that is just disordered. And then at larger the tunings, the theory predicts the appearance of a valence bond solid. So this is a solid phase where you have a little bit of resonances, which means you have a little bit of superposition, but it's not the same macroscopic superposition as in the spin liquid. They're just local. So what you expect to measure for these string order parameters is that in the spin liquid, both of them should be 0. Whereas in the trivial phase and in the valence bond solid, at least one of them should be finite. So this is a place where we are expecting a number, not just that it's finite. So we measured this in our experiment. So here I'm plotting the two string order parameters for Z and X. And what we see here is that for the Z, we basically see 0. This would go up in this area here. It's not plotted, but then it goes down and it stays down. Sorry, that's not true. This should be 0, and it's expected to go up in the valence bond solid, but we don't see it. We don't see it ever going up. Instead, for the X string order parameter, we see that it starts finite and then it goes down, and then it goes towards 0 in this area here, which is actually what's expected for it. One caveat here is that this is true if you take long enough strings. And so here we looked at how this decays when you increase the length of the string, and we see that it goes down as you would expect. Okay, so here what we do is, you see that I identified this shaded spin liquid region. What we did here was to define if there is a range of a range of the tunings in which these two expectation value for the closed loops are finite, and this one is 0. And this is the region where we can say, okay, there is a spin liquid. So summarizing, we put together these three measurements. Closed loops with finite expectation value tell us that we're in a dimer phase. Finite expectation value for X loops identify the presence of a coherent superposition of dimer coverings. And finally, we need to make sure that these string order parameters are 0 in that region to exclude our other trivial phases. So putting all this together, we can conclude that there is a region where we see what we call the onset of a quantum spin liquid phase. Here we use the word onset, that it's been highly debated. What we're trying to say here is, of course, we don't see a quantum spin liquid with infinite correlation lengths. We have some defects in the system, but we do see the signatures of a quantum spin liquid, at least over some correlation length in the system. Yeah. Over space and over many experimental repetitions, yeah. What do you mean? I mean, so what we're doing is we're averaging everywhere. We're avoiding the borders of our array because there you don't have this. You have some, yeah. Anyways, yeah. Mm-hmm. So you only see a deviation when you get close to the boundaries, but in the bulk, it's pretty constant. It's homogeneous over the whole boundary. Across close to the boundaries, basically, you don't really have a spin liquid. You cannot have a superposition because since you have open boundary conditions, there the Rydberg excitations are more localized than they're in the bulk. But other than that, over the bulk, they're pretty homogeneous. The expectation values that we get are homogeneous everywhere. Yeah.
So I had a question which may already be answered on this topic. So when you calculate the de-excitation value for the BBS,
Mm-hmm.
you're averaging over many shocks.
Mm-hmm.
I guess sometimes that value also negative,
Mm-hmm.
negative, the average to zero. But I guess what you're doing here is you're looking at the average of the four inputs.
So when you choose your loop, it should always be the same number, right? Because it only depends. So it should always be +1 if the number of vertices inside is even, and it should always be -1 if the number is odd. So here I'm defining this on a specific, I'm only averaging over the same loop, the same shape of the loop.
But I guess so is it correct to say that for the VBS, you're essentially pulling in some random classical time recovery?
Yeah, okay. So there is a point in what you're saying. I don't know if it's your question, but in the valence bond solid, you should have those first two things being true only for small X loops. So these valence bonds, I mean, we don't really know how they look like because the numerical simulations are on small system sizes, so we don't know how it should look like for larger system sizes, but you're expecting only to see local resonances. So these expectation values should be finite only, for example, if you measure on the single hexagon loop, but if you look at anything bigger, it should go to 0. So we made sure that we measured finite expectation value for larger loops. Otherwise, you cannot say that it's not a valence bond solid. That's a good point. Yeah. Yeah. You're right. I should have put a slide on it and I forgot. So let me see. Oh yeah. So the idea is after we started to take the measurements and we already saw this, we realized that the theoretical paper looked at an approximation of the interaction potential, which is this so-called PXP model. So basically you assume that the interaction potential is infinite within the blockade radius and then it goes to 0 outside. And when they did the simulation on that model, they had these very clean signatures of the spin liquid. But as we were doing the experiments, we were trying to convince them to look at the 1/r⁶ because it changes things. And as they were doing this, they realized that if you take into account enough interaction terms in this 1/r⁶, the spin liquid seems to disappear, and you have a first order transition from the disordered phase to this VBS, to this valence bond solid. Now, the caveat is, so we were very confused because in the experiments we had already seen these signatures. So we were like, if that happened before, we probably wouldn't have done the experiment. But we already had the data. So now there are a few papers that have come out since then that try to explain what should be happening. And the idea is that we're not, doing this quasi-debatic state preparation, we're not able to go through the first order phase transition. These first order phase transition are tough. So we don't end up in the valence bond solid, but we end up in some metastable state that actually is again the superposition of these dimer coverings. So it does have the features of a spin liquid. And I will put the references on the slides. There are a few papers now that have figured out exactly what's going on, doing some more calculations. Yeah. So again, this is okay. So what I just said also explains why we don't see the valence bond solid, because we don't do any further transition into the valence bond solid. In theory, again, as before, it's just set by this ratio. So it's set by the Hamiltonian. In practice, for us, it would be, what we see in the experiment is we see the spin liquid until we go to larger detunings, and then we go out of the dimer phase. So we go beyond this 1/4 density, and so we have something else. So we don't have the topological correlations anymore. What determines that is just the detuning. So at a certain detuning, you're winning the blockade. You're beating the first boundary. Again, this is defined by the Hamiltonian. It's Yeah. So some simulations, if you try, so I'm gonna add that slide. If you try to do numerical simulations where you reproduce the same state preparation as we do, you do see again that the spin liquid reappears. So you do see the signatures of the fact that instead of preparing the ground state, you prepare this metastable state. Yeah, this has to do with the final rate. And they see that the transition is very close to where we observe it. Yeah. No. I mean, basically, it would change only if you were able. So what we see in the simulation is you try to go slower and slower, and what you see is just that the spin liquid becomes better and better, meaning the correlations are longer. But then, you know, I don't think we've ever observed in the simulation that you go slow enough that you actually manage to get into the VBS. You really need to go super slow to go through the first order phase transition. Okay. Okay, I don't have a lot of time, so I'll try to, were there other questions? Okay, I'll try to speed up. I wanted to show you, so now that we have this quantum spin liquid, you can try to use it to make a topological qubit. So what do we need to do for that? I mean, you've seen in the toric code is usually on a torus. In our case, we want to have something with interesting topology. So we basically have a torus or a donut in 2D. So what we do is just to add a hole in the middle. And then when you do this, when you create the hole, you actually turn on the topological protection because you have some non-trivial topology. In particular, this means that your dimer states are now separated into two distinct topological sectors. The idea is if you have some local perturbations, let's say you swap a couple of dimers, you always stay within the same topological sector. But if you want to move from one topological sector to the other, you need to basically move your dimers around the hole. You need to go around the hole to change between these two. So of course, here we have this tiny hole, which means that the topological protection is there, but it's not amazing. But if you imagine a big hole, then you would have a strong topological protection. But anyways, this is a first demonstration. So the idea here is you have these two topological sectors, and you can use them to define your logical states. So the zero state is the spin liquid that lives in one topological sector, and the one logical state is the one that lives in the other topological sector. So you have the superposition of all these dimer states. So what you can do next is to define logical operators. The logical operators are defined like this. Again, here you trust me a little bit. So the Z logical operator is a Z string that connects the hole to the boundary. And if you look at this, you will find that this has, so the 0 and the 1 logical states have minus and plus 1 expectation values for this string. And the sigma X operator is defined as an X loop that goes around the hole. And here you will see that the eigenstates of this operator are the plus and minus states that have plus and minus 1 expectation values. So what we do is we repeat the same type of experiments, but in the array with the hole. And then we measure the expectation values for the logical operator. And we observe that in the spin liquid, we have a 0 expectation value for sigma Z and a finite but small expectation value for X, which means that the state we are preparing as a small but finite overlap with the plus state. So again, here, we still have a lot of technical limitation in the experiment, so we need to do better. But here, the basic idea is there is a first step toward the implementation of a topological qubit with this spin liquid, where the standard state preparation that we do should initialize the plus state. Yeah. That's a very good question. That's a very good question. So that's one of the problems, actually. We can talk about it. I have one more slide that I one more thing that I want to show, and then we can talk about that. So one more thing that I want to show you here is, as I mentioned, we don't see. I mean, we see that the expectation values are smaller than 1, and they also decrease with the loop size. They decrease with the loop size for obvious reasons. If the loop is larger, then you have a higher chance of having defects inside. So this means that, so this has 2 reasons. One, the prepared state. I mean, the Hamiltonian that we have here is not the fixed point Hamiltonian for the dimer model. So even in the theory, the expectation values don't go up to 1, which, going back to your question, means that these X and Z operators that we're defining are not exactly the Z and X operator for that model. And this, I would say, is still an open question. We don't know how to define the proper operators that actually should have plus and minus 1 expectation values. But also, so it's a mixture of these 2 things. We're not in the fixed point, but also we have incoherent errors. Okay, so in particular, let's take the snapshot that I showed you before. You can see that we have defects in the Z basis that correspond to empty vertices. So an empty vertex means that there is a dimer missing. So this corresponds to E anyons. So we can identify these. So these are easy to identify because you just take a snapshot and you look at where you have missing, where you have empty vertices. So here you can build the plaquettes for this lattice. So exactly the same thing that you do for the toric code. And you can build these plaquettes such that measuring the expectation values on the plaquette would allow you to identify if you have an anion. And so you can detect these anions measuring syndromes on the Z plaquettes that are defined like this. And you can do something similar for the other type of errors, which are in the X basis. These are phase errors instead. They're not visible on this snapshot. These basically would correspond to having, in the superposition, instead of having plus everywhere, you have some minuses. And again, here you can detect this by measuring syndromes on the X plaquettes that are, in this case, the hexagons on the Kagome lattice. Here you see something funny that is different from the toric code. The plaquettes are not the same. So that, you know, in the toric code, there are squares everywhere. Here you have this strange thing that these ones have more atoms, they're larger, and so on. Okay, so what we did in collaboration with some theorists at Harvard was to find a way to enhance the detection of the topological order. And here I'm gonna go very quickly, but the idea is to combine local error correction with coarse graining to build basically an RG flow. So the idea is you do a first layer of error correction. So you take your snapshot and you do anion pairing on nearest neighbors. Okay, so you detect, if you detect 2 anions that are on neighboring sites, you annihilate them. And then you do a layer of coarse graining. So now you increase the distance, you go to next nearest neighbors and you do the same thing. You pair anions that are a distance of 2 from each other, and again and again. And at the end, when you're satisfied with this, you measure the expectation value on these string operators. And this is the same thing as measuring these so-called fattened loop operators, where instead of just taking the loop operator, you couple anions at a certain distance from the loop that you're considering. If you do this, now we can basically do just, in principle, you could do this in the experiment if you were able to do mid-circuit readout and feedback, which we cannot yet. So here we just did a simple post-processing using this technique on the experimental data. So let's say we want to measure this big loop. In the experiment here, we basically see nothing. We just see 0. But if we apply this error correction technique, then you see that for an error correction distance of 3, we see that we do recover a signal for the Z loop. Same thing for X. You have this huge loop that we measure here. It was 0 in the in the original experimental data, but if you apply one layer of error correction, you get a finite expectation value. And you can do the same thing on the open strings to make sure that when they're supposed to be 0, they just stay 0. So this is just to give you an idea of something that you can do in post-processing to enhance the measurements of these topological correlations. Of course, it would be really nice if we can do this, as I said, actually on the experiment so that you can correct for the presence of ions. Yeah?
So the readout here is structured to this one.
Yeah.
So when you say error correction.
So there are some tricks that you could play in principle. So, okay, one idea would be you introduce some ancilla qubits. So for example, let's say that you have some extra atoms, you put this extra atom here in the middle, you entangle it with the atoms in the plaquette, you use that to measure the syndrome, and then you apply feedback. So you only measure on the ancilla qubits, so you don't destroy these qubits. It is possible, it's a little bit, futuristic, but yeah, it's exactly what I'm saying. So it's exactly what I'm saying. It's what we're doing here, but here it's just in post-processing. But basically, what you would like to do, when I say here anion pairing, you need a way to detect the presence of the anion without imaging all the atoms, because that would be destructive. And so you can do that by adding these extra ancilla qubits to measure the syndromes and then perform feedback. I mean, it could, so in what we're doing here is just to detect topological order. But let's say that you want to use this quantum spin liquid phase to do something interesting, then you would like to actually correct on it to have a better quantum spin liquid. And so you would like to, feedback and do extra error correction. It's a question if you want to do it. I'm not sure that the answer is yes, but in principle you could. Okay. Yeah. I'll talk about this tomorrow. I'll talk about this extensively tomorrow. Okay, so I'm very late, but let me just mention that. So we're thinking about how to do I showed you that we define these topological qubits and we define the logical states, the operators, and so on. What we would like to do is actually to be able to encode and manipulate the topological qubit further. And this requires the ability to localize and manipulate these abelian anions that exist in this model. And so what we're thinking about is how to do a braiding experiment. But also another direction here is you can actually create non-abelian anions within this abelian spin liquid by engineering alternating M and E boundaries. So basically, if you have an M type of boundary that intersects an E type of boundary, then you would have a Majorana fermion here in the middle, and then you can do some fusion experiments to detect them. This is something that we're also trying to figure out how to do in the experiment, just to give you a quick overview. Okay, here, super fast. There was a question? No. Super fast. Can we do more with topological phases using Rydberg atoms? There have been a lot of proposals for different spin liquid and non-spin liquid phases. I'll need to add a list of those papers. But one idea that I wanted to flesh out very quickly is there was a proposal on how to create a non-abelian topological phase that is the Kitaev honeycomb model. And this requires this Floquet engineering that I mentioned yesterday. So the Hamiltonian that you would like to encode is this one. And as I told you before, as I told you yesterday, it's not easy to have these three different types of interactions, especially it's hard to have them on different sides of the lattice. So to have an anisotropic interaction. So the idea here is, what if we have this lattice and we do this sequence? So we take the two atoms here, we put them close to each other so that they interact, and we perform XX. Then we move them back and we pair the atoms along this type of bonds and apply YY. and then we move them again along this bond and apply ZZ. You do this fast enough, you have this flow K engineering of your Kitaev honeycomb Hamiltonian. This is an idea. I don't know how far in the future it is, but in principle, you can implement the right type of Hamiltonian doing this trick. I think it's a cool perspective, and hopefully we'll be able to do it soon. Do you have 5 more minutes of concentration? Okay. Okay, I just want to show you this because I think, it's a very different thing, but, there have been just a few studies of quantum dynamics, but there is this famous example that is kind of an interesting discovery in Rydberg atom arrays, which are these quantum many-body scars. But also I want to show you this because it has some interesting new tools of measurements. So let me go quick. Who of you knows what quantum many-body scars are? Okay, a good number, very good. Okay, so here I'm not gonna tell you much about these quantum many-body scars, but in 2017, there was this experiment that was where they observed these strange things that in these 1D arrays of Rydberg atoms, after a quench, so they brought the system out of equilibrium, and they saw these persistent oscillations where it looked like the system was not relaxing, was not thermalizing as you would expect. So there were some persistent oscillations that looked odd. After that, there was a lot of theoretical effort to understand what was happening, which connected this behavior with quantum many-body scars. Now, a couple of years ago, we replicated a similar experiment, but in 2D. And the other thing that we added, so again, you prepare your state, then you quench it out of equilibrium, you see some oscillations, and you see how you have your system oscillate between these two ordered phases. You always do this with bipartite lattices, so kind of like the square lattice before. You see that it oscillates between the two different antiferromagnetic configurations. And what we did here was also to add a near resonant drive to see if we could extend the lifetime of these scars. So again, I'm not telling you anything about scars. We just saw that we could stabilize the scars with the drive, but the frequency was changing, blah, blah, blah. What I want to show you that I think it's interesting, and it's related to some questions that you guys asked yesterday. With this experiment, we also introduced some new tools to probe this many-body system. And the idea here is related to this hybrid analog digital method that I mentioned at the beginning. So what we want to do is perform some analog quantum dynamic, move our atoms around, this idea of reconfiguring the array. And then we also do a digital step where we actually apply gates to the atoms. And I'm going to show you now what it could be useful for. So in this case, when you do these many-body scars experiments, you would like to measure the entropy. There is no easy way of measuring the entropy just by taking snapshots in the Z basis. So what we wanted to do was to create 2 copies of the same many-body system and then interfere them to measure entropies. So here's what we do. We prepare 2 copies of our 1D array. We have some many-body Hamiltonian happening. And then we move the 2 copies close to each other. Now they're not interacting anymore within the 1D array, but they're interacting in pairs with their twin atom. And here, what we want to measure is this Rényi entropy that basically corresponds to measuring a swap operator between the 2 twin atoms. Again, I'm not explaining anything, but okay, just to give you an idea. Blah, 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 there is a way we can measure it. So what we're doing is we have the 2 copies, we let the many-body Hamiltonian do its thing, and then we measure the twin atoms in the Bell basis to measure the swap operators. And so here what you see, I just want to show you the measurement. We can measure the Rényi entropy of half of the chain. And we see these, oh, sorry, these 2 are not labeled. So this is for the Z2 state that has the many-body scars. And this is a trivial state where everything is the ground state. So it doesn't have the scars. And so you see the different behavior for the thermalizing state where the entropy increases with time versus the non-thermalizing behavior of the scar state. So this is the end. I just wanted to show you this. I'm gonna show you tomorrow what went behind the idea of being able to move the atoms and do these things. But here I just wanted to show you here what we're doing is mixing analog and digital to introduce new tools to be able to measure observables that are typically inaccessible, like the entropy. For example, something that we would like to do in the future is, can we measure topological entanglement entropy on the spin liquid or something like that? These are things that are typically very hard to measure, but tools like that could give us access to some of this. So this is all. If you have more questions, I'm happy to answer. Okay. Yeah. Mm-hmm. Mm-hmm. So it's an interesting thing because the frequency is not the frequency. It's not the frequency of the drive. Okay, so maybe we can keep going later. But what you see is that the frequency of this oscillation is half the frequency of the drive. But so it's not just the drive. It's not just a simple effect of the drive. It has to do with the fact that you have scars. So it's a mix of the two. So it's just a way to extend the lifetime. But you need the scars to see this effect. If you don't see anything. Mm-hmm. I wouldn't. Yeah, I would need to check what we did, but I think we tried that too, and I think you still see it. We changed the frequency, and I think you can still see it. Yeah. I might have a plot. You see this? Yeah, you see here we change the frequency of the drive, and you see that you get these scars up here. So you can really tune the frequency over a broad range, and you still see the feature. Yeah. So you always get the frequency that is half of the frequency of the drive, but you can tune this. It doesn't need to be a multiple of the frequency of the scars without driving. It can be anything. Okay. Good. Okay. Thank you.